Thank you everyone for tuning in. This is the podcast where we interview working mathematicians to get an insider's look at the way math is done and the mathematical community as a whole. My name is Logan, and I'm sitting here with my partner Michael across from Dr. Brian Edmond Forrest, Professor Extraordinaire of Pure Mathematics here at the University of Waterloo. Dr. Forrest is extraordinarily well received as a professor for his teaching ability, winning numerous awards, including the Distinguished Teacher Award in 2000 and the Canadian Mathematical Society's Excellence in Teaching Award in 2007. Not only is Dr. Forrest an excellent professor, but he boasts over 40 publications and altogether has more than 500 citations. So, how are you doing, Doctor?
Not too bad. You guys have done your research here.
You read your Wikipedia page, basically.
I'm not sure I deserve all that, but...
No, absolutely.
You are the apple of every first year's eye in calculus.
Honestly, I'm so glad that we had you in for calculus in our first year. It was such a nice transition from high school to university.
Absolutely.
Like, you kind of, not to say that you held our hand through the whole thing kind of thing, but you were always there to kind of,
You were the gatekeeper. You sort of demonstrated just how awesome math could be.
I appreciate that.
Absolutely.
That's actually kind of the goal of that course.
Yeah, well, it really is such a very beautiful subject. And so I guess that brings us to our first question then. So we'd like to know, what specifically in mathematics is your field of research, and how would you kind of describe it to a non-math person?
My field of research is known as abstract harmonic analysis. And what that actually means is a little bit difficult to describe, but I can give kind of a historical perspective on it. This, if you look back, it really has an origin in sort of two different disciplines. The first is classical Fourier analysis, which is used to study, which was really invented to study wave phenomena.
Right.
So trying to do things like understand heat, sound, etc. So in particular, if you were to take a sound wave and you wanted to translate what that sound wave was going to be digitally, what you would do is break it up into its various components. And that's essentially what Fourier analysis does. It actually takes complicated functions and breaks them up into various components based on trigonometric or sort of periodic functions, and tries to then be able to reproduce the functions from those particular components. So classical Fourier analysis goes back hundreds of years and was really a kind of a mainstay, and it's still a mainstay in applied mathematics. Its generalizations are still used as part of algorithms for compression and that kind of stuff.
Right.
The second part of the origin of what I do that changes it from classical harmonic analysis to abstract is the fact that my mathematics is based on something called operator algebras, which for anybody that's seen kind of first year linear algebra is a generalization of a matrix, but to infinite dimensional spaces. And the operator algebras were introduced into kind of a physics context to deal with a mathematical foundation for the quantum side of physics. So the Fourier analysis is more on the classical side of physics. The quantum mechanics needs a different type of thing. On the classical side, the fundamental object is a function, and you can multiply two functions together, and that multiplication commutes. And on the non-classical side, the quantum side, you replace the notion of function with the idea of an operator or an infinite version of a matrix, and their multiplication doesn't commute. So abstract harmonic analysis is often referred to as non-commutative harmonic analysis because the objects that we're dealing with, typically speaking, are not algebraic objects that commute with one another. Fundamentally, it's looking at objects known as locally compact groups and studying them through certain analytic objects called Bonic algebras, so different spaces of functions and operators, etc., that arise from the structures of those.
That's a really... Oh, sorry, I didn't mean to interrupt.
No, for me it's interesting because even though I can consider myself an analyst, a lot of what I do is study algebraic objects. So the background is quite diverse. And getting into this area often takes a fair bit of time because there's a lot of different background directions that you need a foundation in.
Right. I was just going to say how it's interesting that a generalization of something that normally deals with functions, like classical Fourier analysis, ends up having a lot of algebra and abstract algebra topics.
A huge amount.
That's really interesting.
Huge amount. All the objects that I deal with it. But I should say that even though I've just mentioned that the origin of what I do comes from two branches of way of looking at physics.
Yeah.
I don't know anything about physics.
Yeah,
so in that sense, you know, I'm a pure mathematician.
Yeah,
that's another really interesting thing, though, is how, you know, these concepts that are really fundamentally physics concepts, then, you know, we get these generalizations and these abstractions that end up becoming an entire field of mathematics in and of itself, and it's just as pure as anything else, like number theory. And
well, I think it's pretty traditional that a lot of mathematics is developed for its own interest's sake, and then it finds its applications after.
Yeah, yeah.
I mean, there's certainly a lot of mathematics that's developed on the spot to deal with real-world problems.
Yeah.
But I mean, historically, it's often the case that a lot of the uses of mathematics come after the discovery, or I guess we'll deal with that question at some other point, whatever, later on. And that's true here, too. I mean, and even in terms of, you know, as separating sort of from analysis to algebra, I mean, some of the kind of places where you get clean cuts are not so obvious to find, right? I mean, there's a lot of relationship between various types of problems that arise in various circumstances. And an algebraic problem might become analytic. An analytic problem turns into an algebraic object or something of that type. So I mean, it's historically lots of strange things happen in mathematics.
Yeah. That's really interesting to talk about, especially the connections between different seemingly unrelated areas of mathematics, like analysis and algebra. In a sense, one is sort of discrete and algorithmic, and the other is sort of epsilon delta E. Not much of an adjective, but
well, but you know, if you look at, like, I mean, I don't know if I should say this, but I mean, you guys were in my Math 147 course. And one of the reasons why we start with sequences is because the idea of a limit in some sense is, I think, more natural through sequences. Sequences are a very discrete process. And if you look at what occurs in the beginning of that course, there's an introduction to things like recursion. And putting that into that particular class is partly to do with the fact that recursive type processes are really important in computer science, but more so because a lot of the use of even continuous mathematics ends up having to be discrete, right? Because the problems in continuous problems tend to not be solvable in closed form, but you can develop approximations, and in many instances, approximations turn out to be discrete. So in that sense, I don't think there's a huge difference between, you know, mathematics that's entirely, well, I mean, there's a difference, but I don't think there's really such a thing as mathematics that never has a discrete component, and mathematics that, in some sense, is always requiring just you to think discrete and never put any kind of term on it.
Not even would you say like something like Galois theory?
Well, I mean,
or I guess number theory is like the classical example of something you'd think is discrete, but then analytic number theory comes along.
Yeah,
right?
I mean, Galois theory has lots of connections in terms of, you know, all kinds of stuff that could be analytic in various ways.
Yeah.
You know, individual ideas, like some, you know, I mean, you can say, well, is a graph, like a graph, for example, a classic example of a thing that you would see in a first discrete math class. But yet these operator algebras that I deal with, one way to actually define operator algebras, and a very important way, is to define operator algebras that arise from certain classes of graphs. You know, but I don't think when people first started looking at graphs, they were thinking of that as in the context of operator algebras. But, you know, people look and they find certain structures that are actually usable, and that comes through at that point.
Just briefly, I remember once I was talking to you last year, I think, and you mentioned that you studied something called amenability theory.
Yes.
Is that too high level to get into, or could you sort of explain how that relates to abstract harmonic analysis?
Well, amenability theory is actually central in what I do. And in fact, a lot of the results that I have in my research area are about if I study locally compact groups. So these are algebraic objects with a topological structure on it that gives them a rich set of analytic objects that are connected with it. And amenability theory is actually reflected in the structure of groups. So for example, if a group, regardless of the topology, if a group is commutative, then it's always going to be amenable. So what does amenable mean? In essence, it says that there's an averaging technique that works in a natural way, so that you have certain functions, and you can take the average of those functions, and you can do it in a way that's invariant under translation. All right, so you think of averaging.
Okay.
You take a function on the real line and translate it back and forth. The average value, in some sense, is always going to be invariant under translation. And that's partly because if we were to put a natural way of determining average, what it actually means on the real line, then in some respect for various classes of functions, it turns out that there's this underlying object called an invariant mean. And that's partly because of the commutativity of the real line. One classical way in which amenability is actually interpreted is through something called the Banach-Tarski paradox, which is the classic case of being able to take a sphere and to pull it apart and then put it back together so you get two spheres of equal volume. One of the reasons you can do that is because there's certain transformations that exist that bring up something called the free group on two generators.
Yes, yeah.
And the free group on two generators, for example, is a non-amenable group. So it doesn't have this property of kind of an invariant average.
Interesting.
And as a consequence of that, you get these so-called paradoxical types of decompositions that are associated with this group.
That's really interesting.
But I mean, there are books of amenability. I mean, there literally are books contained that are 400 pages long, of which they have dozens and dozens and dozens and dozens of mathematical equivalences of the statement of this group is amenable, and all of the generalizations that actually occur beyond that particular point. So it's actually an area of mathematics that has huge implications beyond the type of things that I study. And a lot of really high-level work is being done these days in terms of very complicated groups to determine properties that are connected with amenability. So the so-called area of sort of geometric analysis or geometric group theory really studies kind of phenomena connected with how amenable or non-amenable certain really complicated groups are. So even within the context of the sort of the general term amenability theory, there's literally half an infinite number of ways you can actually study the property.
So basically,
that's really cool. And I think we could probably talk about this for the remainder of the podcast.
As much as I would like to, I would feel bad talking about it without having the background to discuss it appropriately. I would feel sort of like speaking Spanish to someone who speaks English.
Yeah, the technical definition I don't think is really so meaningful in some sense. It has to do with a certain translation invariant linear functional on L infinity of the group, whatever that happens to mean. So
I guess we'll move on. Next question we wanted to ask is, when did you decide that mathematics was the career path that you wanted to follow?
That's a kind of a weird one. When I decided to study mathematics was very close to the beginning of my first year of university. In high school, I wrote some kind of a contest, and I don't even remember really what the contest was, because I was not a contest person. And in the school I was at, contests were just something that you did because some teacher decided, well, we're going to have a group of people write this, and they would force a few people to consider to do it, right? So myself and a couple of other people in our school wrote this contest, and for whatever reason, we did well enough to get some notification or some notoriety in terms of our performance. And as a result, I ended up getting this invitation letter from a professor at the University of Alberta to consider taking the honors math program in Alberta. And I loved math, but I had no idea about doing that. I was going to go into engineering. So I went, the one and only time I ever talked to my high school counselor, I went to see my high school counselor because my math teacher suggested I do this. He thought it was a good idea, but he said I should talk to the counselor. And I mentioned to the counselor, well, I'm thinking about this. And she said to me at the time, I don't think you can actually take math as a single subject. I think you can only, it's part of other programs, part of other things. But you could take like education and become a math teacher. And I thought, well, I got this invitation to actually go take the honors math class. So I was thinking about this, and I came from kind of a working class background, and there you went to university to kind of get a job type thing, right? So being an engineer was what everybody in my kind of scope did if you were good at math. but I didn't want to do drafting because I have terrible penmanship and stuff, right? So, and no matter how much I tried, that's a long story. It goes back to when I was in elementary school. No matter how much I tried, I could never improve my drafting. And I had this immense fear of having to draft all the time. So I decided that instead of going into engineering, I would avoid drafting and I would go into math.
Yeah.
I tried to get into math, and it was a weird thing because originally when I applied, I went in and I changed my application, and then I got rejected from the program. And I couldn't figure out why. And so I phoned them, and they said my high school math marks weren't high enough. And it seemed strange because I had this letter to go into this program from the chair of the department, and my high school math marks were like, in calculus, like one was 100 and the other one was like 98 or something like this.
That's not high
enough. The registrar's office, the person in the registrar's office said, well, that's the only thing I can think of, and didn't look into it. So I actually almost didn't get into the program.
Wow.
That's bizarre. It was very strange.
Drafting the rest of your life.
I would have been stuck
What
drafting.
a terrible fate.
So I probably would have been like designing bridges and things like this was not good for society. You guys have seen me write, so you know that somebody's going to be reading the blueprint and thinking, is that a 2 or is that a 7? So not really the best thing in the world. But eventually we straightened it out, and they actually let me into the program. And to be honest with you, I never really thought about a career as a professional because even when I graduated, there were no jobs. There were no research jobs or academic jobs. It was a terrible time. So what I thought I would do is teach. And but instead of going into, I didn't really want to go into education right away just by itself because you had to do that. I figured I'd combine education and grad school. And my grad department at Alberta was fine, but ed school was resistant. So they wanted me to give up my scholarship and just take education. So instead I just decided to stay at Alberta for a year. I didn't go away because I was thinking, well, I'm not going to do a PhD or anything because there's no jobs, but what can you do? So I thought I would teach. That's what I thought I would do.
I find it interesting that there were no jobs. I mean, like, what did mathematicians at the time really do to support themselves?
Well, research jobs in academia in particular go on kind of cycles. And like I graduated from undergraduate in 1981. So that particular time, particularly in Alberta, was a real sort of recessionary time, but it was a pretty much recessionary time across the board. And what had happened is through the 60s, there was a massive amount of expansion in universities, huge amounts of expansion. So there was a lot of people hired. And that group of people would just be in their 40s at the stage when I graduated, right? So as you're moving through, that whole wave of people was going through, and there was no hiring. Starting about kind of mid-70s through to mid-80s, there was hardly any hiring in universities anywhere, in terms, especially in mathematics. The year I graduated from my PhD, there was only 2 or 3 jobs advertised in Canada that year.
Wow,
that's
crazy.
But there wasn't nearly as many people competing for those jobs. But there wasn't a huge number of jobs. And so when I went into to do my graduate work, it was really thinking I would just do a master's degree and then go teach. And in fact, after the first year of my master's degree, not even after the first year, after the first term, there was a job came up at a college in Edmonton that I applied for. I was just 21 at the time, and I applied for it on a lark to see what would happen. I didn't expect an interview. They gave me the job. So I left I had done all the research work for my master's degree, and I went and took this job at this college. And that job at the college was permanent after a 6-month probationary period. And it actually paid more as a starting salary than university starting salaries were for assistant professors.
Really?
So what was the impetus in going back? And it's kind of strange because after a year there, it was a great job, fantastic job. Lots of fun, lots of interesting people to teach. But I just felt like I wanted to go back and do my PhD. It's kind of a stupid decision in some respects, but it worked out okay.
I mean, you got to do what makes you happy.
I mean, it did. Because I knew I could always go back. Like my boss there said, if you want to come back, you can come back. So
that's a really good situation. Then.
That's like
compared with what a lot of my colleagues were in. Most of the people who were graduating, like after I started my graduate work, a lot of the people who were graduating, none of them got jobs.
Jeez.
Like none of them. None of them got academic jobs.
That's crazy.
It wasn't until my group graduated that the job market started to open up a little bit, and people that I knew who were in grad school started to get jobs.
Yeah, well, that certainly is a scary prospect for sure.
Well, look, you got to be in the right place at the right time, right?
Exactly.
Yeah.
That's the way the cookie crumbles.
And I guess just sort of trust that life will funnel you into the right
Well,
path.
the other thing is, back then, if you went and did a PhD in mathematics, you did it to become a professor. Now, the vast majority of PhDs aren't thinking to become a professor, right?
Yeah.
So there's a huge number of places that are hiring technically skilled people, even with PhDs in mathematics have been going into finance, left, right, and center for quite a while.
That's the big one.
Now that might change, but then maybe it'll be artificial intelligence or something else.
Exactly.
Oh, I mean, AI
So
is already happening.
the whole scope of different things that you could do with a PhD in mathematics has opened up immensely over the 30 plus years since I did mine.
Yeah, I was going to ask if it makes sense that the recession of jobs in that time was sort of due to like expansion in universities. I thought it had to do with like everyone was doing graph theory at the time, and then graph theory fell off, and no one knew what to do that was applicable.
No, I think it was a reaction to the fact that there was a huge number of hirings that happened in a very short period of time.
Okay.
So universities expanded hugely, and then the money to do that sort of dried up, right? I mean, whenever there's a cycle of kind of recessionary type things, public institutions tend to be under lockdown in some sense as far as jobs are concerned.
Absolutely.
So it's always been cyclic.
I see. Okay.
It's been cyclic the whole time I've been in the profession.
Absolutely. Well, again, in kind of like a similar light to this question about how you decided that this was a career path you wanted to follow. I want to ask you what is the first original mathematical result you produced, like even if it wasn't published, just like a minor thing that the first thing you remember doing.
Well, technically, the first thing I did was my master's thesis.
Okay.
But there, I was working on something called semigroups, and I actually ended up with a bunch of results. At that point, like now for us, for example, almost all of our master's degrees are expository. They're one-year degrees and they're expository. Back then, there was a sense, especially when I was at Alberta, there was a sense that your master's degree your thesis should have some degree of originality, but typically speaking, it was usually a fairly small amount of originality, and many of the master's theses weren't published. But I actually published my master's thesis, but not until after I finished my PhD. So
interesting.
And it was partly because, my supervisor picked a good direction, but the first kind of real sort of time I had a sense that I did something that was going to be towards my thesis, etc., was actually about 2 years into my PhD, and I discovered a result that I thought was new, along the lines in the beginning of some of the problems that I was thinking about. And I took it to my supervisor and I said, I can prove this. And again, it was actually this group is amenable if and only if this phenomenon occurs, right?
Yeah.
And my supervisor said, that's a very nice result. Write it up. And I found out about a year and a half later that he had actually proved that result in a paper. Back then it was harder because there was no internet. You couldn't go to internet.
Right.
So you couldn't go to the internet. So the only way you could figure out whether something was there is you had to go to the library and you have to sift through math reviews and read everything under the sun. Yeah. And my supervisor was a great guy, but he was very much, I never knew what he was doing. He kept what he did from his students almost entirely, right? So maybe a year and a half is an exaggeration, but it certainly was probably 6 months to a year later that I actually found out that he had proved that result. But I was actually able to very quickly generalize this much more, and the generalizations became kind of foundational to my thesis.
Okay.
But as soon as he saw the technique of the proof and how I did it, even though he knew that the result was done before, he never told me that he actually did this. So he just wanted me to go with it.
Go and experience it.
Go and experience
That's kind of funny.
Go nuts.
Yeah.
So in a technical sense, it actually is part of my published work from my thesis, but it's a corollary to some other things. So it's a corollary of another way of looking at something that he had done.
Absolutely.
Because the technique was different.
Yeah. So technically, that was the first thing that you ever originally produced on your own.
Yeah.
What about in the way of, I don't know, it might have been different for you because you sort of had a different university life than us, but what about in the way of, I don't know, it might have been different for you because you sort of had a different university life than us, but what about in the way of, I don't know, it might have been different for you because you sort of had a different university life than us, but what about in the way of, I don't know, it might have been different for you because you sort of had a different university life than us, but what about in the way of, I don't know, it might have been different for you because you sort of had a different university life than us, but what about in the way of, I don't know, it might have been different for you because you sort of had a different university life than us, but what about in the way of, I don't know, it might have been different for you because you sort of had a different university life than us, but what about in the way of, I don't know, it might have been different for you because you sort of had a different university life than us, but what about in the way of, I don't know, it might have been different for you because you sort of had a different university life than us, but what about in the way of, I don't know, it might have been different for you because you sort of we've sort of been doing math for a long time in our lives, and we sort of like get ourselves psyched up into thinking, oh, this is a cool result. I'm really going to figure this out. Like, 2 years ago, we were like, oh, the Riemann hypothesis. We could probably do this.
Yeah,
we could probably take this on. Did you have anything like that? Any moments like that in university?
Just, got your head up, dreaming
or
big, and just...
I'll give you an example of something that I was really proud 2 years ago of coming up with this thing, like, about whether a function is easy to determine its nth iterate of. And I was super proud of that result until I realized it was incredibly basic. So if you remember anything like that.
Welcome to Waterloo. No, I mean, I came from a world where academics was pretty foreign. I mean, it was I wasn't the first person in my family to go, I was the second type thing, because my brother went to university. But my interests outside of university would occupy a lot of my time. We worked really hard, and I had a very small class, but really good students. So we would talk about a lot of things, but we usually talked about things that were connected to what happened in class. Right?
Okay.
So exposure outside was fairly minimal, because when we were going beyond what happened in class, it was usually about other stuff. I mean, I coached football, I was a competitive curler. That's the kind of stuff. I had season tickets to the Edmonton Oilers when Gretzky and the boys were there.
Oh, yeah.
So, that's the kind of stuff that occupied my mind outside of that. Math for me was about things I experienced in courses.
I think another thing that, is probably a contributing factor is, like you were saying, like with the internet, right? Like, there's so many resources that even us undergraduates can understand. But if I pick up a math journal, all over my head, I don't understand a word of it, right? But there are a lot more basic, toned down things that aren't good enough to be published, but are good enough to kind of give us a broad understanding of these kind of complex and very deep mathematical results.
It's a huge difference, and because if you have curiosity, you can go to the internet and you can find any level, as you say, of kind of explanation of that type of stuff. So something like the Riemann hypothesis, I don't know when I would have first heard about it. Certainly not before I started university, and certainly not. When I went to university, I had no idea what math was about. I mean, none.
Right.
Really none. I mean, I just liked math.
Yeah.
And I was kind of good at it a little bit, so that's kind of where it was. So it was kind of a leap of faith, but in a weird way, even though we worked incredibly hard, like I worked really hard as a student, I don't think that we had the same sort of experiences as typical here. The exposure to all kinds of different stuff, and it's partly because this program is pretty unique in some respect. There's so many, even as a math student here, when I was a student in Alberta, I took all the math classes that were being offered, with the exception of a couple of applied math classes. But I took every stats class, and I took all the math classes that were offered at a particular level, right? Here, I mean, you couldn't do that unless you're taking 15 classes a term. Yeah. So there's so
Wouldn't
many
be surprised if there's a student out there doing that.
Trying, anyway.
I won't name some names, but I know one or two have tried over the years, despite the fact that I don't think they would recommend doing that again.
But
it's just a different type of experience, and things like math clubs and the Pure Math Club and exposure, undergraduate math conferences, all these kind of things. It just wasn't there.
Yeah.
I had a great undergraduate experience. I mean, it was terrific. I won't be critical of it, and I had some really great teachers. But in the end of the day, most of my math focus was based on things that I saw in class.
No, fair enough. Absolutely.
Yeah. So, what would you consider your proudest mathematical achievement?
This is going to sound corny, but it's actually my students that I've had. No, but really, I mean, to be honest with you, I'm not being sort of falsely modest in terms of my research. In my research area, I've proved some results that are considered to be significant. I don't work in a research area that's considered to be, mainstream, you're on your way to the ICM type stuff. But in my area, I've proved some results that are good. But ultimately, I think most working mathematicians, the biggest influence that they're going to have in terms of what legacy goes on beyond them is the work that they do with students. My grad students have been terrific. I've had great grad students to work with, and some of them are really strong. We have one in this department, Nico Spronk, who was my PhD student. And beyond that, though, I mean, all my students have really been tremendous to work with, and if anything, if I've had some influence with them, that's been positive.
Yeah.
I have results in my area. I mean, I've got certain results about amenability that I've been able to prove, where we solved problems that people tried for quite a few years, and if you ask somebody in my area, they would think it's important. fairly well cited, etc. But I don't see anything that's going to last hugely beyond the time that I'm, sort of active as a mathematician. But that's true of 98% of us, right? It's important that we do this work, but we're fooling ourselves if we think 25 years from now, our results are going to be all that profound.
The next Euclid.
But 25 years from now, my students will still be making contributions. So
absolutely, that's a really good way to think about that. I appreciate that a lot.
Well, and it's at all levels. It's undergraduate students. I have one of my undergraduates is now one of the best young mathematicians in Canada. And it would be arrogant to say that I shaped his career, because there's no way. He was going to be great anyways. But I taught those guys like 5 times, that group 5 times. It was a hugely successful group. And I think there was some influence in terms of just their creativity, etc. But with my grad students, it's more direct, right? And the grad students, it's easier to point. And they're all, generally speaking, my PhD students in particular, have all been quite successful in doing whatever they do. They're all good people too. That's the key thing.
Right. Yeah.
I really like them as people. It's not just they learned mathematics. They're good people. And they help their students, and they do stuff like this. So it's kind of a family in some respect.
And I don't think there's anything arrogant at all about saying that you've cultivated an interest in mathematics and sort of shaped their appreciation of it to a higher extent. Like that's
I mean a part of
that's
it, right?
Great.
You kind of
of course,
people.
no, absolutely. I think every single professor we have in this, kind of journey to get through school, right? I think each one of them, kind of influences how we perceive math and how we appreciate it. And then,
even if it's a negative influence,
hopefully not too many of those.
You know what I mean? I mean, sometimes in the same class, you can have an immense positive influence on one person and a negative influence on somebody else. Somebody else walks away and thinks, "Man, I thought that was interesting. I didn't even like that course." And sometimes, whether it's actually the right way or not, whether somebody really likes a course or doesn't like a course can influence what they do for the rest of their life.
Of course.
I mean, that's how I got connected to my supervisor, who was huge influence, because I loved his courses. His courses were just terrific. And I mean, had it been boring, I'm not sure I'd be doing what I'm doing right now. So.
Absolutely, for sure, definitely. So then, I guess I got to ask you then, because I really do like your answer for what that your students are your most proud mathematical achievement. But then, kind of like the flip side to that question was, what's the one problem that you haven't been able to solve yet, or that you wish you could solve?
Well, there's 2 problems, and there's technical parts of it, but one is kind of a goofy little problem. Well, there's 2 of them. They're both kind of goofy little problems. They don't mean a huge amount in the big scheme of things, but they just bug me. I study locally compact groups, and there's an object called the Fourier algebra, which is a sort of a classical set of, which is an abstract set of functions which come from the results of applying, say, Fourier analysis, the techniques of Fourier analysis to certain objects, but I won't describe exactly what they are. But this algebra has various properties that reflect the underlying nature of the groups. And there's 2 properties that are still that I've worked on over the years that are still kind of open. One has to do with something known as weak amenability, which is not the same as amenability in the same context. It's more a property of an underlying Bonic algebra as opposed to a property of the group, but it's connected to the structure of the group. And there's an old conjecture that I had a lot to do with about the fact that this property would be very much a restriction to the group having to have a very strong commutative component. And that property came from understanding the sort of a new way of looking at these objects, these Fourier algebras, known as operator spaces. And I had something to do with bringing operator spaces into this realm. And so we have a conjecture that now, the last step was Nico and some of his colleagues. We now know that we're just like this far away. I want that solved. Whether it's by me or somebody else, I want that solved. And then there's another one that it's called Aaron's regularity. And what Aaron's regularity is that with these algebras, every Bonic space or every sort of norm space has something called a dual, which is a space of linear functionals. And then there's a second dual. So that object becomes an analytic object, and then there's a second dual. And the structure of the second dual, if you start off with an algebra, so there's a multiplication, and this is topological structure. The second dual inherits 2 natural ways of of multiplying objects in it. And in some classes of algebras, like these operator algebras, those two ways are identical.
Okay.
So it means there's one natural way to extend the multiplication from here to the second dual object. If an algebra has that property, it's referred to as Aaron's regular. These Fourier algebras should never really be Aaron's regular unless the group is finite. So that's a conjecture. And I proved most of that conjecture, and people have moved that close to the point where we now know it would be insane if that's not true. But in order to know whether it's true, it would actually take us into the realm of these really bizarre groups that are connected with the type of thing that I told you about earlier on when I said people are studying these very strange discrete groups.
That's cool.
These incredibly complicated discrete groups. So in some sense, this problem is almost meaningless in some ways in the big picture of things. But it's a little bit like my Fermat's last theorem in the sense that
Forrest's last theorem.
Well, no, but in the sense that it's been aggravating me so long, I just want it solved. So you can get rid of it, right? I mean, it doesn't have anywhere close to the historical connections. But in my world, everybody's saying, well, but this has to be true. And it's just one of these things where, it's just ridiculous. And we've gotten down to the point right now where my whole generation says it's true, but none of us is ever going to be able to prove it. So to a certain extent, that's kind of a secondary problem that I would like to get solved. I don't have any, desire to work on the analogs of the Riemann hypothesis anymore. Because I'm old and I got other things to be interested in my life. So
Fair enough.
At this point, so
out of curiosity, are there amenability theory analogs to the Riemann hypothesis, or at least to other big problems in mathematics that you could share if you knew any?
Well, I mean, yeah.
Are they too dense to get into here?
I think part of the problem would be, in order to translate amenability into areas where that would actually be relevant, I think it would get so technical that it probably wouldn't be of interest.
Yeah. Okay. Right.
But I mean, the problems that these geometric group theorists are working on are deep problems.
Yes. Yeah.
Fundamentally deep problems that have large scale tentacles that go through all kinds of different areas and stuff like that. But if I can't really describe even the definition of what amenability is, to try and translate it into multiple different areas. And some of those areas, to be honest with you, I'm just kind of ignorant of, in terms of how they would kind of play out. Because it is this huge kind of field.
There's no way anyone's going to ever know everything in mathematics.
So, given the context of what you're talking about, I think it would probably be best for me to pass.
Fair enough.
All right, fair enough.
So, what about, more simply, do you have a favorite theorem or a most beautiful property in mathematics?
I do have a favorite theorem.
Okay.
And it's the bare category theorem, which you guys have experienced indirectly already.
Really?
I feel, was that the question with the F sigma and G delta sets from 147?
Very much so. It was the question about whether or not a function, if you can have a function that's continuous on the rationals, but discontinuous on all of the irrationals.
Yeah.
So that question, the solution to that question is an application of the bare category theorem.
Okay.
And a bunch of students in class kind of, I think, definitely with the help of the internet, because you could get a sense. Like, I'm not saying people just went and got the answer off the internet, but you could see that people got ideas that they put together. Yeah. So I've been giving that question for years, and it was, for years, nobody came close to answering it. I had one kid who was actually in physics, and he came up with this beautiful answer to the question that was related to the idea that if you take a series with terms that go to zero very rapidly, so like if you take the series 1 over k factorial, that sums to e, and that number is going to be irrational, right? And you can prove it's irrational just using the series decomposition, and it's partly because the terms in the series go to zero so quickly. So he basically took that construction and he built inside of every little interval, numbers that would have a particular property that had to be irrational. So he actually did this barehanded. And there's an essence of that in terms of the solution that a lot of people got to this question in your class with some help from the internet. But he did it well before the internet was supposed to be. But the thing about the bare category theorem is I have this little book written by a guy by the name of Oxtoby, and it has all these wild connections between the bare category theorem and all kinds of different little problems in mathematics, etc. But it's just a fantastic theorem. Like, it's a great theorem. And it's a theorem that you would experience in Pure Math 351. But it has all kinds of wild implications.
Interesting.
So probably, in terms of a theorem that kind of, at the level that you guys could understand.
Yeah.
That's probably the theorem that I would say is my favorite.
Yeah,
Very cool.
What about things that, anything particularly shocked you in your research or in your understanding of mathematics? Something that you saw that was like, that can't be true, but after wiggling through it, it became true.
Well, I mean, I think the answer is yes, but not so much as profound as that. But,
Okay.
I spent some time when I was a student looking at sort of set theoretic things. And some of the wild stuff that has to do with sort of consistency and independence of various axioms of set theory. Like, it's still a mystery to me how somebody, like Cohen, for example, could come up with these types of results. Cohen, by the way, was a harmonic analyst. Like Paul Cohen.
Oh, interesting. Huh.
Yeah, the guy who proved the independence and consistency of the continuum hypothesis. So,
Right.
like, he was actually a harmonic analyst. He worked.
Really?
His first recognition, he won something called the Bachner Prize for his work in harmonic analysis. And actually, there's a lot of Cantor was also a harmonic analyst.
Wow.
Because what ends up happening is some of the problems in harmonic analysis that become extraordinarily difficult to really solve are that way because there's these underlying sort of set theoretic connections that make them sort of profoundly difficult to look at.
That's
right?
bizarre.
And so I guess there was a few times when I looked at kind of the connections between set theory and other aspects of mathematics where I just thought, man, this is just ridiculous. So
that's crazy.
I knew I didn't want to do it.
Yeah.
But I thought it was pretty ridiculous.
Wow. Yeah.
Well, I know you mentioned Cantor there, and I'm just wondering, like, who are like your mathematical heroes from like history?
From history?
Yeah,
oh,
or living. I mean,
well, living would be my supervisor, Tony Lau. I mean, he was undeniably the major influence of my mathematical career. He's a professor at the University of Alberta, and I ended up doing all my degrees there, kind of by fluke, partly because of this issue of going to this college and coming back and then ending up staying. I was actually thinking of going to Berkeley, but it just didn't seem to work out, and I stayed there, and he was such a fantastic supervisor, but also just a fantastic person. So if I have any success in mathematics in my career, it's probably 97% of it can be traced back to his influence. And in terms of like my answer about students, like that would come from him too. He's a terrific mathematician. I mean, he's got hundreds of papers. He's been incredibly influential in our area. But if you asked him the same question, I guarantee you he would give the same answer. I don't think that's any question. And he's cultivated kind of that attitude amongst all the people that he's worked with over the career. I mean, one of the things that I knew from him was once you go out there, you've benefited from people being kind to you and people helping you along.
Yeah.
Pass it forward type thing.
Absolutely.
And that in our community, Tony's had a huge influence. He's produced a lot of students. He's one of probably, I would say, maybe next to George Eliot, had more PhD students over the last 30 years than any other Canadian mathematician, pure mathematician. And a huge number of his students have gone on to academic careers. But it's remained kind of a family, and everybody helps one another out. We share a lot of stuff. People are very cooperative in terms of giving students chances to come speak, postdocs, etc. like that. So, I mean, without a doubt, Tony would be the number one.
Yeah.
Historically, I don't know, maybe Carl Weierstrass, maybe.
Yeah,
Okay.
He was pretty cool.
He's
all right.
I mean, he was...
I'd have a beer with that guy,
Riemann, I mean, they were kind of responsible for changing the math, the math culture in terms of how it's presented. To the point where it sort of influenced the way I look at things. I mean, an analyst, because I like that stuff, right?
Right.
I like that.
I mean, Weierstrass was one of the first guys that showed that there was a function that's continuous everywhere, but not differentiable anywhere. Right?
Absolutely, yes.
Yeah, that's
by construction, and that was historically important part of the way that analysis is kind of done these days with the sort of formality, because that was a problem that people thought for many years such a function couldn't exist. And there's a connection there again to the bare category theorem, because one of the consequences of the bare category theorem is to show that amongst all continuous functions, say on a closed interval like 0, 1, that's the typical function in a categorical sense.
Okay.
So the bare category theorem says that in this space of all continuous functions, the nowhere differentiable functions are actually what we refer to as second category, which means that the thick in that set.
Mm-hmm.
And the functions that have a derivative at even a single point are first category, which means that from a structural perspective, they're kind of negligible.
Okay.
Okay. How would you describe your philosophy of math?
Man, I don't know.
I know, that's an open-ended question.
It's pretty open-ended. We had it kind of broken down into like a couple sub-questions. So I guess, like, would you describe yourself as like a Platonist? Or, like, do you think math is out there and it exists?
I've thought about this a lot, because I get asked this question a lot, and I've had some interesting students who have debated me on both sides of this. I think it's a little bit of both. I mean, in some ways, there are a lot of objects that look like they've been constructed.
Mm-hmm.
Yeah. And there's bridges that you have to build and things like that, right? But man, it's just hard to believe that the way things fit together, that there isn't some kind of object that exists out there just to be discovered. So I'm split. I think that parts of mathematics are discovered and parts are actually invented.
The best way that I've had it, like, I've thought about it and I've had people, discuss it with me, is it's kind of like we invented the axioms we chose, and then from that, everything else was a discovery.
Yeah. And that's part of the reason why, at least in my opinion, math seems to line up so nicely with physics and the real world and things like that, because everything is chosen initially in a way that describes or reflects reality. So,
yeah, but I think it's even more complicated than that, because you ask yourself, like, where do the axioms come from? And some things, in some certain circumstances, are considered to be axioms, and other things can be discovered. So it depends on where you start, right? I mean, like this goes back to the idea of sort of set theoretic stuff, and what are the minimal sets of things that you can do, like do you accept the axiom of choice or not accept the axiom of choice?
Exactly.
And like, that's a weird thing, because if you said to me, do you accept the axiom of choice? I'd say absolutely. But if you said to me, do you accept Zorn's lemma as an axiom? I'd say no. But yet we know they're the same. Well, because if you think about Zorn's lemma, the axiom of choice feels very much like, if this wasn't true, then there's something wrong with the world. Zorn's lemma doesn't have that feeling when you first discover it.
Yeah,
right?
I guess.
Zorn's lemma feels like a result that you would get from something else. But yet they're logically equivalent.
I guess so. I'm trying to think of
a weird duality of, like, if you look at these problems with different perspectives, they seem more or less likely.
I'm trying to think of like a physical analog of the statement that all vector spaces have a well-defined dimension, because that would be an application of Zorn's lemma, right?
Yes.
So in that sense, it's sort of like Zorn's lemma is just a stepping stone towards another thing that you can accept. But I can't think of a. Oh, that's hard.
I mean, there are lots of equivalences. There are lots of partial equivalences. There's these kind of things. And that's kind of what I was talking about when I started looking at the set theoretic stuff, it kind of got, this is pretty goofy. How would anybody ever really... You're going to sit there, and no wonder guys like Cantor and whatever got really intensely disturbed by some of these questions. Because,
absolutely.
It gets to the point where I guess I have a little mind, so I like to leave that to someone else. I got too many other things in life to worry about. I don't need to worry about that kind of stuff. Maybe that's a cop-out, but...
No, there's nothing... I mean, I see people say, like, man, I wish I was smart enough to have an existential crisis. You're just smart enough to realize that you don't have to be happy.
Well, but, I mean, if you talk to a concert pianist or something like that, or somebody who composes music, I mean... Is part of the composition process? I mean, is there? I mean, it would be hard to imagine that there isn't some sort of governing body that determines underlying structure of music. I don't know anything about music, but yet one wouldn't suggest that people are just entirely discovering music that was out there. I mean, there has to be a combination of the kind of the tool part of it that you need in order to be able to use your creativity plus the creativity side.
Absolutely. I think that's a pretty apt.
It's hard to say.
Yeah.
I mean, can you paint the Mona Lisa if you got my hand skills? I don't know. You're not going to do it just strictly with technical skills, but if you got my abilities on the wall, the Mona Lisa ain't coming out.
Some art galleries do. You would be surprised.
Yeah, I mean, I've been to lots of art galleries, and there's some stuff that maybe might be that. But the Mona Lisa, I've been to the Louvre. The Mona Lisa ain't coming out of these houses. I'm telling you that. That's just the way it goes.
Well, now, for those people who are listening and maybe haven't taken 147 or any of your classes, I know you've mentioned a lot of times that, you know, your day kind of starts at 4 a.m. Like, that's when you get up.
It's usually 4:30.
4:30.
But it had been 4 for a while, but now I'm 4:30.
It's, well, treat yourself, sleep in a little.
What have you been doing actually lately? I got up at about 5:15 today.
That's still many hours
Sleeping
before
in.
I got up.
Have a late night or something?
Yeah.
No, I was just tired.
Fair enough. But I mean, it does beg the question. I mean, what do you do with your whole day, right? Like, what's a day in the life of Dr. Brian Forrest?
Well, it depends on the time in my life. But right now, my wife and I are developing the online versions of Math 137 and 138.
Okay.
And this is a ridiculously time-consuming process.
I bet.
So the day for both of us is pretty much, we get up early, we start working. You know, we go through, write course notes, put together potential planned lectures. I spent a good part of the last term in the recording studio, like probably 3 days a week. I was in there from 8:30 until 12:30, you know, just recording lectures, etc. You guys saw in 147 some versions of, not the ones that we did last term, but those were done for a different course before. Okay. So in the last little while, I've been doing a lot of online stuff, and it's very time consuming. And because I've been teaching online a lot too, I'm online a lot. And when I teach the courses in this Masters of Mathematics for Teachers program, they're all over the world, and they ask questions, and I'm usually online, so I'll answer them. So it occupies the day. You know, if I'm doing research, that tends to be a little bit more structured. I'll work in a more structured way. But right now, it's kind of, you get up, we work on these courses, we see where we get. You know, in the past, when I was an administrator, life was different, because I've been in a department chair and done other stuff. I go to meetings. I like, as far as productivity is concerned, the early morning stuff is nice, because nobody bothers you. So I can get up, I can do things that I wouldn't have time to do in a day when I come into the university and I've got 19 people that want to meet with you. You know, so having been an administrator for many years in my career, it just became sort of a defense mechanism for being able to protect time.
Okay.
But it's also partly because I always got up early, so.
I see.
I don't know, it's pretty boring in some respects.
I think you ask a celebrity what their day-to-day life is, and they'd probably say it's boring as well. You know, I had cereal this morning. Like, what do you want to hear from Tom Cruise? Right?
To give you sort of a strange sense, like, you know, I mean, the Math 147 last year, the first term course, the first course was at 8:30 in the morning. So you'd think that would be right in my wheelhouse, right? I mean, you're up at 5 or 4:30 or something. Yeah. But it felt too early for me. You know, it was weird, because I'd come in here, and I'd get here usually around 7:45. I'd go down to the course usually around 10 after 8 or so, and answer questions, etc. But the students often were not yet awake in the same way as they were in the afternoon class. You know, so one of the strange things is that teaching for me is a later activity. Like, the earliest I'd like to start teaching is 9:30, but I kind of like the idea of 10:30 to sort of 2:30. That realm. So it depends on what task there is. You know, and like that, my day is sort of dictated by whatever I have in front of me, and depending upon what's in front of me, it changes in terms of when when I'm active and when I'm not.
Yeah. Okay.
Absolutely.
You mentioned research. I just wanted to ask, what was your research technique like? I often hear, for example, on the Academia Stack Exchange, that it's often like you're trapped in a brick box and you're bashing your head against every brick wall.
You know, it's kind of like that in some respect, but for me it was always, I mean, it's kind of propagated on, like, I used to read a lot. Like, I used to read a lot of stuff. And you'd see a certain germ of an idea, and it would be, okay, I think there's a connection between this and something else. So then it's a matter of being like a dog with a bone and trying to trace it down as far as you could possibly go. But a lot of it for me was really just using instinct. You know, to a certain extent, if I've contributed anything in my research field, it's not necessarily always been that I've solved problems, but I've often had a pretty good idea about what I thought the solution should really look like. So in some weird ways, it's really based on instinct. This has a feel about it. And roughly through my career, most of the time, my feel has been accurate, or at least it's taken me far enough when I actually discover something that I say, no, this is different. So, you know, like, this idea of operator spaces, one of the results that we were trying to prove that turned out to be connected with one of the things I would say was one of my favorite results, was that these Fourier algebras had this property, this Bonic algebra version of amenability. And for a long time, we sort of felt like that would happen if and only if the underlying group was amenable. And there was lots of natural reasons for why that should occur. So that was a problem I worked on for quite a while. And I understood a lot of the connections as to why this should really occur.
Yeah.
But it wasn't happening. Like, we couldn't figure out how to do this. And there was, you could get it to the point where, and if you could just prove this, then everything would work. And surely this must be true. But then there was this little paper written by a fellow by the name of Victor Lozert, who's a brilliant guy. And this paper was an old paper, and it was pretty unknown. And in this paper was kind of the germ of the idea that if things weren't commutative, something bad would happen.
Okay.
And that was kind of a click that all of a sudden turned my whole feeling about this is probably not going to work. And what actually, well, it wasn't quite at that time, but what actually occurred before that was this fellow, Jean-Jean Rouen, in the University of Illinois, proved a result that showed that if you added this additional structure of operator spaces, that you could get the result that everybody was trying to get. But Lozert's result, connected with what Rouen did, gave me the sense that this isn't going to work. Because in the Bonic algebraic setting, without this additional structure, this thing is a fundamental obstacle for what seems to be driving how his proof works. And that was really the trigger for me that operator spaces could live inside of our research world. And it turned out that operator spaces actually really profoundly changed the way that people in my area thought of these objects. But that wasn't like some profound, deep understanding of operator spaces, because I hardly knew anything about them at the time. It was more just a sense that, there's this quirky thing in the back of my brain that somehow I knew we needed to do this. And just reading this one piece, these two papers that seemed to have nothing to do with one another, showed that they were in conflict.
Interesting.
And so, if there's a technique, I don't know if there's a technique there, but that's been kind of my research career. Moments of that particular type.
I imagine it's probably do you think it has something to do with the fact that harmonic analysis and I guess functional analysis in general, a lot of the arguments are, I don't want to say intuitive, but they sort of follow naturally, as opposed to something like, at least I've found in combinatorics or in number theory, for example, a lot of the arguments end up being really dense or otherwise technical.
Well, there is in my field too, and I'm not great with dense and technical. So to be honest with you, in terms of my career, the answer would be yes. Now, I mean, it's not to suggest that, you just look at it for 30 seconds and it fills out.
Everything's trivial.
But I mean, the way that I approach mathematics is very much like that. It's top down, right?
Yeah.
So there are people for whom, there's a fellow, Charles Reed, who unfortunately passed away recently, who was insanely brilliant at coming up with counterexamples to things that people couldn't solve. And his technical skill in constructing these counterexamples was immense. But in his career, as accomplished as he was, he had very few points in his career where he actually kind of developed any fundamental theory. He was just a machine in terms of coming up with these insane counterexamples. And there was another fellow in Bonic algebra theory who was kind of the inspiration behind this notion of amenability for Bonic algebra, is Barry Johnson. And Barry had both skills. Barry had incredible instincts, but could, in fact, really do amazing technical things.
I see.
So he, for example, actually showed that this amenability would not happen for certain types of amenable groups. And he did that on the Fourier algebra. And he did this by reinventing the wheel for lots of things on the Fourier algebra that we all knew. So, I mean, his paper was a strange paper because it was spectacularly surprising from our perspective. But on the other hand, there was lots of stuff in this paper where he just needed the technique, so he built it. And it was known, but he didn't know it, right? So on one hand, he had the right intuition, because he just understood the subject, to know the right direction to go, because we were all trying to prove that something was true, and he showed it was false. But it wasn't just technical precision, but he had to have exactly the right instinct in terms of where to look. And he really, his work with Rouen's work with this result of Lozert really painted the entire picture for why these operator space things were sort of a fundamental characteristic. And then we later discovered that the operator spaces there was a reason why the operator spaces were hidden. It's because a lot of what we do comes from classical commutative harmonic analysis, and it's problems that relate from commutative harmonic analysis. When you go to the non-commutative case, the answers can be different, but often there's kind of a meta theory that guides what's going to happen. And it turns out that in the commutative case, this operator space structure was there, it's just hidden because it's trivial.
Oh.
But if you analyzed the proper analogs and you put this operator space structure in, a lot of the theorems that were all of a sudden we couldn't prove, and now all of a sudden the operator analogs come through, they really are, the operator space analogs really are the right objects, because this structure was there, it was trivial in this particular case.
Wow.
But it still had an underlying role. It's just that the role was not apparent because of commutivity creating kind of this weird kind of simplicity in terms of stuff that happened. And there's a notion called Pontryagin duality, which says that if you've got a commutative locally compact group, there's a natural dual commutative locally compact group. And commutative harmonic analysis takes certain classes of function algebras and translates them through by a Fourier transform or Fourier-Stieltjes transform. And in the non-commutative world, there's no natural dual group, but it turns out that these Bonic algebras that we've studied have a dual property that really is a generalization of Pontryagin duality.
Interesting.
And it comes from the existence of this operator space.
Wow.
Underlying structure. So we know a lot more about that now.
Fascinating.
Yeah.
Okay.
I'd probably be lying if I didn't say that the only thing I took away from that is how to pronounce Pontryagin, but...
And who knows if I've done it correctly.
Yeah. But,
well,
yeah.
We're just about out of time now, because we're running out here. We don't want to take up too much more of your day, but we do have one more question for you. And, like our year in particular, it set an unprecedented amount of people going into the 140s, and there's a lot of people that are really interested in pursuing pure math and going into academia later on. So, as a professional mathematician yourself, we were just wondering if you could bestow any advice onto us as we go through our.
The only advice I can give you is follow your heart. This goes back to this decision I made of leaving that college. Why did I make that decision? I really don't know. It just felt right at the time. And when you're young enough, and if your responsibilities are minimal enough that you can take a risk like that, sometimes you have to do that. But where you get to, what I would say is don't try and plan out the rest of your life too early.
Yeah.
Especially with respect to things like being an academic, because it's a challenging route, and sometimes it's just a matter of being in the right place at the right time. But any student who looks at it and says, the only thing I ever want to be is a professor, I would seriously say to that student, you better rethink that particular idea. It's great to say I really want to be a professor and I'm willing to dictate myself to that goal, but anytime you say this is the only thing that I can imagine doing, it's a challenging route to get through.
Yeah.
Experience as wide a variety of different things as possible. Work hard and don't give up, but don't narrowly focus on something to the point where it just becomes too much of a consuming issue.
Okay.
Right. Well, no, that's very important. Yeah,
I'm not really that good in giving people advice like this.
No, that's really good advice, because there really is there's not a lot of jobs in academia at any one time. You can teach math till the day you die, basically, right? So
yeah, but you can do math too. You don't have to, it's one weird thing. It's a strange thing. I think I would have always been interested in doing math. It just would have been different.
Yeah, absolutely. For
sure. And I'm seeing more and more nowadays people that go to college or university to get a certain degree and then end up having a job completely far removed from whatever they studied.
It was always true.
Yeah.
It was always true. People used to talk about the burger flippers who would do arts degrees and stuff, right? But in reality, there was lots of evidence that suggested that people who did arts degrees did very well after the fact. It's just that, the idea that somebody was just going to go there and waste their time, it just wasn't true. Even on an employment level, it wasn't true. It was true often that people who did arts degrees, their salary levels would be less than, say, somebody who did engineering or a more technical discipline. But job satisfaction was often higher. For many years, they would do these surveys, and people would find that they would use their skills in ways they didn't anticipate.
Yeah.
But you study history. It's not like there's a million jobs out there saying wanted historian.
Yeah.
The people who understand the perspectives of history can work in all kinds of different jobs.
Absolutely.
And they can use what they've learned there, and they can use the reading skills, they can use the communication skills, they can even use the perspective that you get from understanding mistakes that have happened in the past, and all the rest of that kind of stuff. So, same thing with math. I mean, you can always having some mathematical skills is never a bad thing.
Absolutely not. Yeah,
Absolutely.
Especially in this ever technologically advancing world.
Absolutely.
I would say,
Absolutely.
maybe amenability theory tomorrow is going to be the next AI. You never know.
It could have some implications. on AI.
Elon Musk's next company, OpenAM, Open Amenability Theory.
There you go.
Yeah.
Right.
Okay.
All right. Well, thank you so much for coming
problem.
on.
Yeah, absolutely. Thank you so much for, once again, being our guinea pig on this first podcast. It was an absolute pleasure speaking with you. So
I'm a shy guy, but I can talk.
yeah, well, it was
No,
great.
you did
I
a
think
very good job,
it
yeah.
couldn't have gone better. So once again, thank you so much.
No problem.
Thanks, sir.